Dear students, welcome you all to this video lecture. This is N. Manikandan, Assistant Professor of Physics from Government College of Engineering, Pune, Naikelu. In this video lecture, we are going to see about the topic non-uniform bending. This topic belongs to first unit properties of matter in the paper Engineering Physics PH8151. Okay, let us move to the topic. Non-uniform bending. What is non-uniform bending? Suppose we take a beam AB supported horizontally on two symmetrical knife edges like this. O is the midpoint of the beam. Now apply a load at the midpoint. What happens? The beam bends like this. At the center, depression produced. This type of bending is known as non-uniform bending. Why do we call this non-uniform bending? Because bending of the beam does not form an arc of a circle, and the radius of curvature of the filament is not same in the beam. Now we can easily define what is non-uniform bending. That is, if a beam is loaded at its midpoint, the depression produced does not form an arc of a circle. This type of bending is known as non-uniform bending. Okay. Now we are going to derive the expression for Young's modulus of a beam using non-uniform bending method. Look at here, beam AB is horizontally supported on two symmetrical knife edges C and D. Distance between the two knife edges is L. E is the midpoint of the beam. Now we apply a load W at the midpoint. The beam bends like this. At the center, depression Y is produced. Here, the force acting vertically, the force W acting vertically downward at the point E, the force of reaction split into two parts, W by 2 at C and also W by 2 at D. This force vertically acts vertically downward, and the force of reaction split into two parts acting vertically upward at the knife edges C and D. We know that the cantilever problem. In a cantilever, one end of the beam is fixed and the another end of the beam is free to loaded. Look here, this point is considered as fixed point. The length of the beam is L by 2. And this is the free end, the load W by T is applied. That is, here two inverted cantilevers present here. So to derive the Young's modulus value, we consider the cantilever problem. In cantilever problem, the depression Y is WL cubed divided by 3YI. Give equation number 1. In our cantilever problem, load is W by 2, length is L by 2. So, in the cantilever expression, the value W by 2 is substituted instead of W, and the length value is L by 2 instead of L. That is W by 2 into W by 2 whole L by 2 whole cube divided by 3yi equal to W L cube divided by 48yi. Rewrite this equation. Capital Y equal to W L cube divided by 48yi. Equation number 2. Where capital Y is the Young's modulus of the middle of the beam. W is the applied load. The W is equal to mg. M is the mass. G is the acceleration due to gravity. L is the distance between the two knife edges. Y is the depression produced at the center of the beam. This is the expression for Young's modulus of the middle of the beam. Special cases. Suppose we take a rectangular beam of breadth B and thickness D. Look here, this is the cross-section view of the rectangular cross-section view of the rectangular beam. Therefore, for this dimension, geometrical moment of inertia value I equal to BD cubed divided by 12. Substitute this geometrical moment of inertia value in equation 2. We get capital Y equal to W L cube divided by 4B D cube Y. This is the expression for Young's modulus of the rectangular beam using non-uniform bending method. Suppose we take a circular beam of radius r. This is the cross-sectional view of circular beam of radius r. For this dimension, geometrical moment of inertia value is I equal to pi r power 4 divided by 4. Substitute this value in equation 2. We get capital Y equal to W L cube divided by 12 pi y r power 4. Give equation number. This is the expression for Young's modulus of a circular beam using non-uniform bending method. Okay, let us move to the next topic. This is the experimental procedure. This is the experimental procedure to determine the Young's modulus of a material of a beam using pin and microscope method. This is an experimental arrangement. That is, a rectangular beam AB is supported horizontally on two symmetrical knife edges K1 and K2. At the midpoint, a weight hanger is suspended, and also at that point, a pin is fixed vertically, and the tip of the pin is focused by a traveling microscope. Look at here, this is a traveling microscope. This traveling microscope have two scales, that is horizontal and vertical vernier scales. Here we use vertical vernier scale. Distance between the two knife edges is L. The initial reading on the vertical scale of the microscope is taken. A suitable mass is added to the hanger. The beam depressed like this. The cross wire of the microscope is adjusted to coincide with the tip of the pin, and the reading of the vertical scale is noted. For increasing the load value step by step, the traveling microscope readings are noted, and also repeat the experiment for decreasing the load. From this table, we can calculate the value of mean depression value y, and we know that the distance between the two knife edges is L. This is a rectangular beam. The breadth of the beam is measured by using vernier caliper, and thickness of the beam is measured by using screw gauge. From the values L, B, D, using those values, we can easily calculate the Young's modulus of the material of the beam by substituting those values in this equation. Capital Y equal to mg L cube would be 4b d cube y Newton per meter square. Here capital M is the mass, this is the acceleration due to gravity. From this relation we can easily calculate the value of the Young's modulus of the material of the beam. Okay, thank you.